Okay, so this is the prep video for sections 4.1 and a little bit of 3.7. So again, the point of this is for you to watch the video in its entirety, do the practice problems, the prep problems for class. Those are the easy ones, so that way you kind of get a good handle on the easy material, and then we'll extend those concepts in class and spend all of our class time on the harder material, hopefully with the idea that it'll make it easier for you. So all of Chapter 4 is about using the first and then later the second derivative for getting information about the graph and about rate of change and some business applications. So first, let's remember what we know. We know that derivative is slope. Okay, so let's remember some definitions that we have. Increasing. We say a function is increasing when it has a positive slope, and so a positive slope. So a positive slope in terms of the derivative then would be f prime of x greater than 0. We also clearly would then have decreasing. You would imagine correctly that it has a negative slope. That means the graph has a negative slope at that time. But because we're talking about the slope of the curve as it moves, again, we're talking about derivative, so in this case, it would be less than 0. We say that a function is constant when it has 0 slope. So again, the derivative equal to 0. So what we know about a function like here, it's decreasing, and then starts increasing. So we can see a graph changing, and now we can write that in terms of the derivative. Okay, so let's take a moment and think about just a very simple curve. Here's an upside-down parabola. Here, on this side, we find that the function is increasing. And here, it's decreasing. We always read left to right, just like we read English. We read graphs left to right as well. So that means here, so increasing would be the derivative is positive, and decreasing the derivative would be negative. Well, between positive and negative, where do we go through? 0. And so in point of fact, right here, that slope is 0. Okay, that makes some sense. So let's do a little bit of a summary table over here. If the derivative, so we'll have derivative, f of x, the graph, oops, I'm running out of space, try that again. So let's say that we found the derivative, and we plugged in a value, and we find out that the derivative is positive. What does that mean? That means that the function itself is increasing. It means the graph is rising left to right. What kind of shape could that have? Well, it could be a straight line, or it could kind of shallow out like that, or it could rise a little bit more and then tail off. So these are all three different shapes for how a function could be rising. Which of these shapes it is, we'll get to next class, and it will have to do with the second derivative. All right, so let's finish this out. If we have a negative first derivative, that means that the function is decreasing. It means the graph is falling, again, left to right. And so it could fall in a straight line, it could fall kind of shallow again, or it could fall like that. So again, the curvature part has to do with the second derivative, but just the rising, falling part has to do with first derivative. So let's take a look at this one here. This is actually this is figure 7 on page 243. And so it just shows a lot of different ways that a function can be. So here it's decreasing, and then here it becomes 0, the slope. And then it starts decreasing again. It gets to the bottom, it's 0. It starts increasing. It gets to the top, it's 0. It starts decreasing. Here, it's actually infinite slope, right? It's undefined because it's a cusp. Here, it's 0 again, so we have increasing, 0, increasing. Again, another cusp in the other direction, and then decreasing. And here, Just nothing, just decreasing. Okay, so let's look at this. We can look along and say increasing, decreasing, 0, undefined. But let's talk about then, we can actually label another set of points. This point right here, we would call a local min, a local minimum. And we know that happens when we have a decreasing function, it hits the bottom, and then it increases again. So any time that the derivative goes from negative to positive, we will have a min, a local min. And then here, the reverse. That's a local max. Anywhere kind of in the area, it's the highest point. So this would be a local max. So what happened here? The derivative was positive and then switched to negative. So any time that the derivative goes from positive to negative, we know we have a max, a local max. I don't expect you to, don't memorize this. Don't do that. We're gonna use your favorite, sign charts. Sign charts will make it readily apparent what's going on. So I just kind of summarize this here, but please don't memorize that. All right, so let's look. Are there any other max and mins on this point? And there are. I mean, on this graph, I see one here. That's a min. And I see one here. That's a max. So what is the derivative at those points? At those points, again, we go from negative to positive or positive to negative. But here, instead of the derivative being 0, here it's undefined. So that's starting to sound a little bit suspicious. What do we know? We know that to have a max or a min, I'm running out of space. We know that to have a max or a min, so this means to have a max or a min, and the general word we use for that is extremum. Extrema with an A is plural. So a max or a min, some extremum. Then if we look at that, it requires that the derivative is 0 or undefined. That should sound familiar. Where else have we put numbers on a number line when we were looking for places where a function was 0 or undefined? That's exactly a sign chart. And so we are going to be able to summarize information very compactly in a sign chart that will tell us lots about the graph. Okay, so a couple of questions. So this then would be a partition point. Let's just reintroduce that name. The partition point is the x values that makes the derivative 0 or undefined. So here's a question. What happens if, because it does happen on occasion, what happens if this partition point is not in the original domain for the original function? Then clearly you can't have a point there. If you don't have a point there, you can't have a max or a min. So a max or a min occurs when the derivative is 0 or undefined and that x value is in the original domain. So altogether, the points that are partition points for the derivative, that means where the derivative is 0 or undefined, and at the same time are in the domain, we define those as critical points. So a little bit of a difference. I say critical values often, but critical values or points. So a little bit of a difference. A partition point is anywhere where the derivative is 0 or undefined. Critical values are only those values that are also in the domain. Okay, so that means we are going to have a process. So let me write this up. It's called the first derivative test. So here's the process we're going to use. So the first thing is to find the derivative. And then we're going to perform a sign test, or a sign chart. So what numbers do we put on a sign chart? Zeros, we're going to give a solid line. Asymptotes I usually write that way. If you happen to have a hole in the graph, I would write it that way. What values go on? These would be all the x values that will make the derivative equal to 0 or undefined. So basically the numerator is equal to 0 or the denominator is equal to 0. And then we're going to check. We're going to check signs. If we have positive, negative here, the derivative, and I would label these because we're going to have multiple sign charts, so go ahead and label. This is a first derivative sign chart. If it turns out that when we evaluate it, it's positive here and negative here, that means you can actually draw these arrows. It goes up and then comes down. So clearly that's a max. You can imagine that it does this. Down and then up. Clearly that's a min. There are cases also where maybe you have plus plus. Well, that's kind of interesting. That means it goes up, it flattens out, and then goes up again. No max or min. And the same would be true if you had minus minus. It comes down, flattens, comes down some more. Again, no min or max there either. So if the first derivative changes sign, one way or the other, you know you have a max or a min, and just draw the arrows. It makes it very easy. So let's do some examples. Here's example 1. F of x equals 3x cubed minus 9. So we want to know, the question would be, tell me where it's increasing, decreasing, and where it has a max or a min. To find out all that information, increasing, decreasing, max, min, all of that comes from the first derivative. So that's the first order of business. So clearly 9x squared, very easy. Now I want to get a sign chart. So I want to set this equal to 0. That only happens when x equals 0. So for this particular problem, x equals 0 is my only partition point. And in this case, is it also in the domain? Yes, so this is also a critical value. All right, so let's start plugging in. Say minus 1 plus 1. Negative 1 squared is positive. Positive 1 squared is positive. So what is this one doing? Up, flattens out, up again. So is there a max or a min? No. So no max or min. Is it decreasing anywhere? No, not decreasing at all. So it is increasing. Now we have to be a little bit careful. Increasing means rising. It is not rising at this point right here. So I can't say it's increasing for all reals, from negative infinity to infinity. I have to break it up right here at 0 because at 0 it's flat. So that would mean I would be increasing from negative infinity to 0. Hold off the 0 because it's not increasing at that point, and then never decreasing. So again, first derivative, figure out what, set it equal to 0, solve for x, put that on the number line, plug in your points. Please label it f prime. I promise you that will help later. You could draw some arrows to kind of get a sense of what it's doing. Clearly, no max or min. Increasing here and here, but not right here at 0. Okay, let's do another one. Okay, so you're probably looking at this thinking cubics. That's a mess. Remember that as soon as you take the derivative, all of these go down by 1 power. So while the original function may be a cubic, we know that the derivative will be a quadratic. Well, we can handle quadratics, no problem. So doing the derivative, negative 6x squared plus 6x plus 120. All right, now we do need to set this equal to 0. Quadratic set equal to 0, our first order of business is to factor. The first thing we always do is factor out anything common. So I'm going to pull out a negative 6. That means I have x squared left here. Divide this by negative 6, negative x. Divide this by negative 6, negative 20. So negative x, I'm seeing 4 and 5. I think that should work. This is how I factor. I know I'm going to have x's. I think 4 and 5. Now I put in the signs. I want more negative than positive, so negative here, positive here. Okay, so this does not give me x equals 0. I've seen that a couple of times. This is just a number, and it's a negative number, so we need to keep that, we need to bear that in mind because that's going to affect where we say it's increasing or decreasing. This one tells me -4, and this one tells me 5. Okay, so I'm going to come over here on the other board and make more space. Okay, so, actually maybe I can fit a little bit here. So I need to get a, no, let me do it here. I need to put everything on a number line. So what goes on the number line? -4 and 5, not this. So -4 and 5. These are partition points. Are they also critical values? Yes, they are in the domain, so let's go ahead and give them some solid circles. Let's pick some points to try. And start plugging in. I always like plugging into the factors. I find it faster because we just deal with the signs. We don't worry about the actual value. This is going to contribute a negative sign to every single computation. So if I put in -5, I get negative, negative, plus the negative out front, 3 negatives, negative. I put in 0, I'm going to get negative, positive, negative, negative, positive, negative. And I like to actually write them kind of in the order that I see them. So if it's 3 multiplied factors, I write them across like that. If I put in 6, I get negative, positive, positive. Okay, so I forgot. Let's label this. So now let's look at what the derivative, what the function is doing. This means it's coming down, going flat, going up, going flat, going down. So clearly then we can see where it's increasing, decreasing, max and min. So let's go ahead and write those out. So increasing, -4 to 5. We don't include the endpoints because the derivative is 0 there. Decreasing, -infinity to -4, together with 5 to infinity. Where do we have a local max? That's where it goes up and then comes down. So the local max would be at x equals 5. If the problem says what is the local max, then you need what is a y value, where is an x value. So where is the max? The max occurs at x equals 5. What is the max means I need to come back in here and plug in, which I didn't do ahead of time, so I'll let you do that if you like. Where does the min happen? That's where it goes down and then goes back up. So that min happens at x equals -4. Does this, and again, all the way along, all of the problems, all the information that you've ever learned about how to handle any polynomials should all tie together. So let's come back to this original problem. This is a cubic, and this says that it's the equivalent of opening down for a quadratic. A regular cubic, x cubed, looks like that. If we have a negative on the front, -2x cubed plus some other stuff, that means it's going to start like this and go like that, roughly. Just, I don't know, something like that. Is that about what we have? We go down, we go up, we go down again. Down, up, down. So yes, that makes sense. So it's always worth making sure everything works together. Oh, excuse me. Okay, here's one last problem. A rational function f of x equals x squared plus 4 over x. Okay, so it's the same process, derivative, sign chart, and then interpret the sign chart. So first for our derivative, we see that this is a quotient rule. That's okay, we can still do quotient rules, chain rules, all of that still works. Those are just more complicated derivatives. So here we'll have bottom times the derivative of the top minus the top, please use parentheses, times the derivative of the bottom, all over the bottom squared. All right, so let's clean up. I'll get 2x squared here. I'll write it out. 2x squared minus x squared minus 4 all over x squared. Or, let me write it over here, x squared minus 4 over x squared. So finally, x x minus 2, x plus 2, all over x squared. You are going to need to factor top and bottom, so just go ahead and be ready for that. Now I'm going to set this equal to 0. So remember, for the sign chart, I'm looking for every x that makes the derivative 0 and undefined. So here I'm going to get from the numerator 2 and negative 2, and from the denominator 0. So 2 and negative 2, those are points on the graph. This one's not. So I'm going to write it that way just to kind of reinforce to me what I'm looking at. And again, let's label. Okay, so we need to pick some. It's time to pick some values. Minus 3, minus 1, 1, 3. So if I put in negative 3, I get negative, negative. This one's always positive. So negative and negative. If I put in negative 1, I get negative, positive, always positive. If I put in 1, I get negative, positive, same thing. If I put in 3, I get positive, positive, and the denominator is always positive. Okay, so looking across, I can see that it goes up, and then it goes down, asymptote, it goes down, and goes up. So now we can write our increasing, decreasing max min. So increasing would be from negative infinity to negative 2, together with 2 to infinity. Decreasing. Everywhere it's negative 2 to 0. Again, something happens at 0, so I can't say it's decreasing all the way through. So negative 2 to 0, together with 0 to 2. Max. The max happens at x equals negative 2. And actually, this is one, let's go ahead and figure this out. So x equals negative 2. If I put a negative 2 here, I get 4 plus 4 is 8, divided by negative 2. Negative 4. Min is going to happen here where the function is going down and then coming up. So the min will happen at 2. The local min, 4 plus 4 over 2 is 4. It may strike you as strange that the max is at a lower value than the min. Remember that these are local maxes. They're not absolute maxes for the entire function. So let me think if I know what this looks like. I don't know what this looks like. I'm going to try and draw it off the top of my head just quickly, but I don't have that. Okay, so, but just so to bear in mind that these are local max and min. Yeah, it looks like this. So it looks like this, and then like that, I think. So here is the local min, and here is the local max. It looks something like this. Okay, so that's all for section 4.1. So again, this is first derivative test. You have the function, you find the derivative, you do the sign chart. So first you find the values that go on the sign chart. Again, we're looking for pluses and minuses. Figure out where it's increasing, decreasing. Arrows are helpful. They very clearly show you where you have a max and a min. And so that's it. So do all of the problems that pertain to this one. And then for section, the bit from section 3.7, I'm not going to explain where this comes from. We'll do that in class. I know this is going to be a little bit strange. I just want you to have some practice with computing something called the elasticity. It's fairly easy to do. And so we will explain more about what it means and how we're going to use it when we get to class. I just wanted you to have some facility with computing it. All right, so I'm going to define it for you. This is the elasticity of demand. E of P, E, very creative, elasticity. It's going to be minus P times F prime of P all over F of P. Okay, so how will we set this up? So an example would be the following. You have a price-demand equation given by this. So remember, P is price, X is demand. And in this case, the problem is 1,000 times 40 minus P. So we need to compute E of P. So we're going to have P's in here. So this one is set up fine. So this is actually our function of P. So the elasticity of demand, negative, P times the derivative of this. So we may want to then, before we get to this point, actually write out that derivative. Let's do that. So F prime of P, 1,000 times derivative of 40 is 0 minus 1. So the derivative would be negative 1,000. So now let's look at finding E of P. Negative P times the derivative F prime of P, negative 1,000, all divided by the actual function. Where's that? Here. 1,000 times 40 minus P. All right, let's clean this up. Minus times a minus, positive, 1,000 in front. These are multiplied factors, those thousands, so they do indeed cancel. So we get P divided by 40 minus P. And it's fairly common for it to work out to a simple, fairly simple fraction like that. Okay, so now what we're going to do is we're going to, so this is just how you compute it. So the negative sign, the actual variable P, the derivative over the function. What happens if you don't start with this? What happens if you start with P equals something or other X? And that's okay. If you start with P equals, you just need to solve for X. P needs to be your variable here. So you want a function of P. Now, once you've computed this, what does this mean? Well, I'll explain more in class, but for now what I'd like you to know is the following. We're just going to define what it is. So if it is a value between 0 and 1, we call that inelastic. More details to come. If it is exactly equal to 1, then we call that unit elasticity. And so remember, these are pertaining to demand. In class, we're going to talk about what happens to revenue, but for now, this is what we're talking about, just demand. And then if it's greater than 1, let's see, what do we think? Inelastic, unit, I'm thinking elastic, and that would be correct, elastic. Okay, so let's find some. Let's find some values here. We're going to do 8, 30, and 20. So E of 8. Just plug in 8. So 8 divided by 40 minus 8, 8 over 32.25. So where in the table does this fall? Right here between 0 and 1. So this one we would say that the demand is inelastic. All right, let's try E of 30. That would be 30 over 40 minus 30. 30 over 10, yes, 3. Where does that fall? That falls here, greater than 1. So we say that this is elastic demand. And then lastly, E of 20 would be 20 over 40 minus 20. 20 over 20 is 1. Clearly, unit elasticity. So for the assignment, for the basic prep assignment, you just have a couple of problems where you actually have to compute this E of P. I believe one of them you actually have to solve. You're given something that's not solved for X. So remember, you always want to have it solved for X in terms of P. So a couple of problems where you compute this, plug in some numbers, and determine what category it's in. So I just wanted you to have some comfort.